आवाज आएगी, नहीं तो कुछ भी बोलोगे आवाज आएगी, भले ही मैं इसमें हूं ना। स्टार्ट। Hello everyone. Sorry for the interruption. Actually, due to the network issue, the connection was lost. We are now reconnecting to our audience. So I'm requesting the speaker to start the session. Dr. Ravi, you are requested to request the speaker or connect him on the phone. He has not joined on the Google Meet. कौन सी मीटिंग है? लिंक भेजो दोबारा से। He has not joined. वो ज्वाइन कराओ ना, लिखो YouTube पे ज्वाइन करो, एक सबको कहो गूगल मीट पे सर दोबारा करो, दोबारा गूगल मीट पे।
You are not allowing me from that side. No, no. Okay, just give me a minute. No, it's fine. So, are you getting it? Okay. 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 So, sorry, friends. So the whole momentum is now disturbed, and now I was talking about rule of mixing, rule of reciprocal, rule of mixing again. So these are the ways by using micromechanical analysis I can calculate the properties of the lamina. But here, while I am calculating the properties of the lamina, I am considering and accounting the fiber volume concentration, matrix volume concentration, as well as the matrix properties, fiber properties separately, individually. That's why I call it microanalysis. I can calculate E1. E1 is the Young's modulus in the direction of the fiber. E2, Young's modulus or the stiffness in the direction transfers to the orientation of the fibers, Poisson's ratio, and then I have the shear. So I will just skip this slide. I come to nanocomposites quickly. Now, what is nanocomposites? Why we are talking about nanocomposites? Because now when I am dealing about nano, this nano word means nanoscience, nanotechnology, nanometer. So the nano means the reinforcement. I was talking about how I can classify a composite. I can classify composite based on matrix. Again, in nanocomposite, I can also classify a composite based on matrix, based on reinforcement, the geometry of the reinforcement. My dear friends, we can use this concept over here. Nano means at least one dimension is in nanometers. Some of the nanofluids I am showing you over here: graphite, graphene, carbon nanotubes, HBN nanosheets, HBN nanotubes. These are some of the nanofluids that are commonly used for the manufacturing of nanocomposites. Nanoclay. Nanoclay is also one of the nano reinforcement. Graphene, you can see over here on the top left. What are these balls? These balls are carbon atoms. These balls are carbon atoms. What is these rods in between? I am representing the carbon-carbon bond, the covalent bond, by using this beam-like structure. In between these here, left, extreme left, the right one, I am direction. Direction is showing, if you see, this is representing a red, red, red. If I am moving like this, the structure that is formed is referred as armchair. If I move the opposite direction, perpendicular to this, I will call it zigzag. You can see this, it's moving in a zigzag manner. Tuck, 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 left, right, left, right, left, right. I call it zigzag. So it means if I apply the load in this direction, I will call it armchair. If I apply the load in this direction, I can call it zigzag direction. If I put 1 million graphene sheets, what is the thickness of the single graphene sheet? Thickness of the atom, angstrom. I am talking in angstrom region. Thickness of a carbon atom is the thickness of the graphene sheet. But if I put 1 million graphene sheets, one over the other, tuck, 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 what I will get? Graphite. I will get graphite. A pencil graphite, the same graphite I am talking about. But when I am dealing with a single layer sheet, it's graphene. Then why this graphene nanofibers I'm talking about? Because it is having an extreme strength, extreme thermal conductivity. Why this is extreme strength? Because I am dealing at the atomistic level, and carbon-carbon bond is one of the strongest bond in the world. So when I'm talking about this single sheet of graphene, I am talking about carbon-carbon bond. Carbon nanotubes, when I roll this graphene sheet to make it a cylinder, I am talking about carbon nanosheet. Here is a comparison about HBN nanosheets and graphene, one of the two of the more commonly used 2D nanofluids. Color one is black. Young's modulus. What is the Young modulus? Terapascal. What is terapascal? What is the Young's modulus of steel? Young's modulus of steel is 210 GPa. What is the Young's modulus of graphene? 1 terapascal. Can you imagine 1 terapascal? How high it is as compared to steel? Tensile strength. Normally, every metal has a strength in megapascal. But when I am dealing about these nano materials, what is the tensile strength? Giga. I am talking in giga terms, not in mega. So now instead of MPa, now we switched straight away. We raise the properties in the level of gigapascal, shear modulus, gigapascal. What is the thermal conductivity? Extremely high. Thermal stability, oxidation, and all these properties are governed when I am talking about the thermal stability. So it's very high. What is nanocomposites? What is composites? I clearly gives a definition and a difference between these two over here. What are these two? In composite, I clearly mentioned that composites are multi-phase materials in which constituents are combined in such a way that they keep their individual phases separable. Nanocomposites are a class of materials in which one or more phases with nanoscale dimensions, as I mentioned in my previous case. There can be a different applications of nanocomposite, and now these days government have a separate section in DST, Nano Mission, which is specifically funding projects or specifically focusing the research that is based on nanomaterials. Nanocomposites, I explain you. Microelectronics, biomedical application, drug delivery, we are using this. Hydrogen storage, we are using these nanomaterials. Water purification, desalination, this is one of the area where I am focusing my research these days. One of my doctoral students is working on water purification. I am using these nanomaterials, nanosheets, because of its high specific strength for desalination purpose as well. What is over here? Graphene nanoplates. How many graphene plates are there? Sheets are there? 1, 2, 3, 4. I have 4 graphene plates. What are these? Polymer chains. What is the stiffness of a polymer chain? It is very low. I can make nanocomposite in these 3 manner: phase separated, intercalated, exfoliated. The exfoliated one is the one I need it, because each graphene nanofiber is uniformly dispersed. I want it to be properly dispersed in the material so that I will get a uniform and a homogenized properties, because in my second and first case, I will not get all the benefits of the nanofibers because it is stacked. Because of this stacking, instead of improving the properties, sometimes it starts degrading the properties. I want it to be separate out like this. It is something like that. If we are making some chapatis and we are making some this atta, what will happen if we put some salt in it? If salt is accumulated in one place, it will only degrade the taste. But if it is uniformly dispersed, we will get perfect taste. Same thing is over here. Nanofillers should be perfectly dispersed. So I need means to disperse it in the polymers. This is one of the basic requirements for nanocomposites. Different people study nanocomposites by using different means. What does it mean? I explained you earlier characterization technique, experimental techniques. Can you see this small nanofiber? Nanofiller, carbon-carbon bond. What is the length of carbon-carbon bond? 3.3 angstrom. Very small. What type of machine I need? I need very expensive machine. Even then, I cannot calculate and measure the tensile strength. I need very high range, high costly machines. So most of the research that is focused on nanocomposite is based on computational mechanics. FEM based. Earlier we start with FEM based because finite element is the most commonly used softwares in 1950s or 60s. We are using finite element for aerospace industry. So we use the same concept of finite element. What exactly we did here in modeling a graphene sheet, you can see a graphene sheet over here. I model carbon-carbon bond as a beam element. The strength between the carbon-carbon bond is modeled or simulated by using a beam element, whereas the carbon atoms becomes the nodes. I hope that you deal with finite element. You know what are nodes, what are elements. On the extreme left and bottom side, you can clearly see the elements, the beam element between two carbon-carbon atoms, whereas these circles are representing carbon atoms that are replaced by nodes. So this is one method how we can. When we are modeling nanocomposites, carbon-carbon, I need material properties. I need material properties to be simulated. I need material properties because when you did finite element, what are exactly you need? You need K matrix. F is equal to, what is that? Kx is equal to F. This is the equation that we solved in finite element. What is K? This K matrix is referred as stiffness matrix. What is the stiffness matrix? This is the matrix that depends, the property depends on material properties and the geometry. From where I will get the material properties? You will get the material properties of these bond, because what is this beam? Beam is representing a bond, covalent bond. I will get these properties from micromolecular mechanics. How this bond will behave by using this potential energy concept. Here I am assuming that this bond is behaving like a spring. What is the force of a string? Energy stored in a spring, half kx square. So I am doing the same thing. I am representing this bond by a spring, and I am calculating this. So I am just skipping this because I lost already many. I come to this non-bonded interactions. I hope you understand. We all learn in our 11th and 12th bonded interaction, non-bonded interaction. Carbon-carbon bond, covalent bond. I will represent it bonded interaction. What is the non-bonded interaction? When I say one graphene layer and I will put one over the other graphene layers and I make millions of stacking of the graphene layers. What exactly get? Graphite. How these two graphene layers are in interaction? How the interaction is taking place? Is there any covalent bond? No, there is no covalent bond. So what type of bond is there? Non-bonded interactions. I hope when I say the term, what is non-bonded interaction? I will say van der Waals interactions. Have you heard about van der Waals interactions? Yes, we heard it. So scientists, researchers also simulated van der Waals interactions by using beam elements, different as spring elements, or maybe truss elements. Here on the left, multi-wall carbon nanotubes. Here in a single wall, the carbon-carbon bond is represented by beam element. What will happen with the stacking of these cylinders? How these one cylinder is interacted with the other cylinder? It is shown on the extreme right. Two cylinders, one in the center. You can see over here my cursor is moving. Second one is outside. So the red ones are the non-bonded interaction, which is shown in the magnified view. I took this from the work of Professor, I forget Lee, Professor Lee and Chow. He did a very pioneering work in the year 2003, where he said we can model by using molecular mechanics. Now again, characterization techniques, I skip. Why atomistic modeling? But now these days, because the computers are coming, workstations are coming, and people are modeling these nanomaterials In atomistic modeling, they say, okay, finite element is giving a very global properties, but these atom bond breaking cannot be computed or simulated using finite element. How these bonds will break, when they will break, what is going to be the strength? I cannot model it by using finite element, which is continuum mechanics based principles. So I moved to the atomistic modeling. Now these days, most of the scientists are working in the area of atomistic modeling. I am also working in atomistic modeling. This is a new emerging area. How atomistic modeling is emerging? Because now these days we have good workstations with having a RAM of 500 GB, multiple processors, hundreds of processors, and I can do it. What is the why we are using atomistic modeling? Unique properties of these nanomillers are due to their atomistic structure. Why this graphene having a very superior strength? Because the carbon-carbon bond, the strength of this carbon-carbon bond. Defect in these nanoparticles can only be modeled at atomistic level. Suppose if I remove one carbon atom from this whole graphene sheet, can I model it on a continuum level? I cannot. I cannot do it at finite element level. But at atomistic level, I can do it because I am dealing with atoms. I can easily replace one atom. Molecular dynamics is one of the techniques which are used commonly these days for the modeling of nanomaterials. What is molecular dynamics? Just one line. Molecular dynamics is solving the second law of Newton's. Force is equal to mass into acceleration. That's it. If I solve and integrate, I can write F force is equal to mass of an atom into d square r by dt square. D square r by dt square, which is representing by this acceleration. If I want to know what is going to be the distance or what is going to be the position of my atom, I just need to integrate it twice. This is molecular dynamics. I know the position of the atoms. When the atoms are very much close to each other, it starts repel. Atoms are far away, it starts attracting. But when atoms are in neutral position, it is experiencing neither attraction nor repulsion. This is the position which gives me the minimum energy. So I am looking at these concepts by using Newtonian equations of motion. I am skipping these slides. I am just coming to this slide. What exactly is this? This is a work of one of my PhD students. He was recently received Fulbright Fellowship. What exactly he did? He modeled a polymer chains in atomistic level. On the extreme layer A, you can see PE, the black-gray screen. It is polymer chains. And what exactly that colored region in between? This colored region is showing I put our nano sheet in between. And I studied what will happen if these sheets, instead of have defects, instead of having a perfect sheet. Because when I'm modeling, I always consider assumption sheet is perfect, polymer is perfect. I'm not considering, I'm not doing. I am working with the more practical aspects. My sheets is having some defects. What will happen? I show in my research, instead of using a sheet without any defect, if I have defects, the defects have better interaction with the polymer chains and it has a better reinforcement capabilities. The nanocomposites have a superior strength. So the conclusion of my presentation is, in this case, also again one of the research by Akash Verma. It published it in Applied Surface Science. Again, the yellow region, yellow sheets, it's graphene. What is this colored surrounding it? Polymer chains. So it means I am reinforcing. I am modeling it at nanoscale, atomistic scale. I am dealing no continuum, because continuum will give me a perfect global properties, but it cannot give me the localized properties. The strength of these nanomaterials are governed at the atomistic scale. I again reinforce it, and I again concluded from these results here. Improvement in tensile strength as compared to P. It means when I am talking about grain boundaries, that means I am talking about defects. More number of defects, the superior is the strength. So if I am using a defective sheet, what will happen? It is only not only improving the strength of the nanocomposites, but also reducing the cost. I am not worried about making a nano sheet without adding defects. If it comes with a defect, I am happy. Price is low, but my work is better because my nanocomposite that I am developing is having a superior strength as compared to the pristine one. These are some of the results I am showing on the slides that shows clearly that, okay, I have a nanocomposites which is having a superior strength. Now you can clearly see how this nano sheet is bending when it's having defects. The defects make these sheets bend. So this is some of the examples that I have from my own work that I performed in nano level at the atomistic level. I am skipping this thing, and finally I am concluding the overall presentation. I can say composites are right now in an advanced stage. Composites are right now in an advanced stage, and we are already using it in aerospace, and even we are using it for more conventional applications. In earlier years, because composites were very costly, so we were restricting it in applications where cost is not the concern, like defense, aerospace. Cost is definitely not a concern. But now these days, when the composites are available at lower cost, we are using it for the manufacturing of pressure vessels, pipes, sports gadgets, automobiles, many applications. Then when we are switching to nanofillers, I can say nanofillers have excellent mechanical and thermal properties. Due to their exceptional properties, they are having a numerous applications that we are generating from nanocomposites. Computational means are also available because of the superior computers, supercomputers. We can model these systems at the atomistic levels. And finally, I will say thanks to all of you for hearing me patiently and staying with me for the last 1.5 hours, and even also absorbing the power interruptions along with my lectures. Thank you. Okay.
Thank you very much, sir.
Thank you. You are welcome. You are welcome. Sure. Yeah, sure, sure. Please, please, please. Quickly. Corrosion resistance of metal matrix hybrid composites. So basically, when we are talking about corrosion, what is the reason behind corrosion? The reason behind corrosion is when we having cells, chemical reactions that is taking place, and these chemical reactions that is basically eroding my material in corrosion. So when we are talking about reinforcement, hybrid reinforcement, what is mean by hybrid reinforcement? This means that instead of one, we are using multiple fibers. We call it hybrid reinforcement. Earlier, if you see or saw my examples, I was talking about glass fiber, and the other one is carbon fiber, but I'm using single fiber. So it means when I'm talking about hybrid fibers, I am using multiple fibers so that one fiber can have the mechanical strength, whereas other can help us in improving the chemical reactivity. That is one of the reasons we have some composites, metal matrix composites. This is the way we can improve both of them. As such, I am not an expert on metal matrix composites, aluminum composites, these composite magnesium based composites. When you are talking about corrosion, I will give you one good example. Magnesium based material composites. Where we are using magnesium? We are using magnesium because of its biodegradable material properties in orthopedic implants. But what is the negative aspect of this? Because it is having a high degradation rate, wearing. So what exactly we are doing? We are using protective coatings. This is one way we can improve the corrosion and the wear. Protective coating. There are protective coatings on the metals composites. We are using this method for corrosion resistance. Protective coatings that includes nanofibers. Thermal coatings that includes nanofibers. So the coatings are one of the best ways to improve the corrosion resistance as well as wear resistance of these metals. We are using it for magnesium based bioimplants. Next question. Trapologically, I am really sorry, but I am not an expert on that area. Types of nanoparticles. Okay. When you are talking about nanoparticles can be of different ways. If you remember, during my presentation, I mentioned two of them. What are those two of them? I say carbon black, one particle. I call it carbon black particles because it is spherical. Other word is nanoclay particles. These are the particles When I want to talk, I mentioned it geometrically. I can classify it. So I have nano black. I can consider this as a nanoparticle. I have nano clay. I again classify it as nanoparticle. Then I have nano sheets. I classify it as 2D nanomaterials, graphene, HBN. I have 1D, one dimensional. What is one dimensional? Carbon nanotubes. Because the diameter is fixed of these nano sheets, only I can vary the length. That's why I call it one dimensional. So these are the three classifications. These are the examples of 1D, 2D, and particles. Next. He's following my paper on MD. Which paper he's talking about? Have you any idea? Because I published more than 50. Okay. Okay. No problem. I will explain it quickly. I hope this is the last question. Oh, okay. So when Nimesh, his name is Nimesh? Animesh. So the answer of the question is when I am talking about atomistic modeling and you want to couple it with finite element. My dear Animesh, there are two ways to couple it. And we call it multi-scale modeling. Why? One scale is at atomistic scale, nanomechanics. Other scale is at continuum scale. I call it continuum mechanics. These are two different scales. I cannot straight away go and couple it. The stresses that we are measuring at the continuum scales are Cauchy stresses. The stresses that we are measuring at the atomistic scale are real stresses. Different ball game. So what exactly we are doing? We are doing multi-scale modeling. What is multi-scale modeling? When we are coupling two scales. So there are two means to couple these scales. What are those two means? One is sequential multi-scale modeling. Other one is concurrent multi-scale modeling. Sequential multi-scale modeling means first I perform my atomistic simulation. I calculate the properties that I need. Then I feed that property in a second stage in finite element model. I call it sequential sequence. I first perform this and then I go to the other one. Example, if I suppose I want to calculate the property, the bilinear property or the interface between two materials, I want to calculate what is going to be the strength of this bimetal interface at continuum level. At atomistic level, I calculate the properties of the interface. I calculate the properties of the interface. I calculated it by using traction law. When I calculate and develop a traction law by atomistic simulations, I call it atomistic simulations. Have you heard about bilinear traction, exponential traction law? I use the same traction law. I develop and gather the properties, parameters that I need to define that traction law from my atomistic simulations. Now I have that traction law and I feed it into the continuum model. Cohesive elements. What is going to be the properties of my cohesive element? That I defined using my atomistic simulation, that I extracted from my atomistic simulation. I call it sequential because one sequence is followed by another one. Another method that you are asking about is concurrent one. I am running an atomistic simulation and in parallel, I am running a molecular finite element based simulations as well. I call it concurrent one. Now the forces and displacement that I am calculating at the atomistic level are now feeding directly, exchanging, interlinked at the same time in my finite element. My mesh at the interface is of the same distance as I have in the atomistic simulations. So this is the way I can couple by using two different means, sequential, concurrent, for my multi-scale models. So there is a lot of work that is going on. Recently, I published a paper in Journal of Applied Physics that is related to sequential multi-scale model. You can refer it. The author of the paper is Mr. Prince Kumar Verma. He's one of my master's students. So you can refer that paper that gives you more explanation. Okay. What you say is beggar. Uh, no, he want to use it in Metal bio. I really don't have any idea for that question. Application of composite in future, I will say many applications. You have to decide yourself. You have to decide yourself where exactly you want to use it. If I start, I will say lawn tennis racket, but now these days I will give you one good example of nanocomposites and composite both. One example is when we are talking about defense. I give you an example. I was working on this project in John Hopkins University in USA for army applications. Space structures, definitely we have many applications in space, but in army, have you heard about this vehicles, UAVs, which carry army person from one place to another place in Afghanistan, in Jammu and Kashmir, in our areas that is having Naxals? What will happen? Landmine blast. What happens with the landmine blast? The church is blown up. Enormous amount of heat is generated, and it comes inside the cabin. What happens? A lot of casualties. So what now our people are doing right now these days? They increase the thickness of the belly above changes. They put steel billets. Why? So that the thickness is increased, steel billets. What will happen if anything, suppose bomb explodes, mine explodes, what will happen? That thickness will absorb some of the energy, but because the steel and these metals have very high good thermal conductivity, still some of the heat is got absorbed in the cabin, and it is really enormous. What exactly other disadvantage that we have? We have another disadvantage. I will clearly mention that the weight of the vehicle is changing because we are putting steel plates just to having some safeguard against the landmarks, but we are not playing with the engine. Engine capacity will remain the same. We are replacing now all these things with a composite plate. Composite plate are bad in conductor, thermal conductor. So that problem is solved. Having exemplary strength against compression. My second problem is also got to be solved. Now we are working on this aspect. One example is this of about composites. When I am talking about nanomaterials, the best example that I can give. Have you heard about stunts? These days, bypass surgeries are replaced by stunts. Now, stunts are manufactured by using different materials. Nickel is one of that materials. Now, researchers are also looking to coat this material with nanomaterials like graphene, carbon, these things. This is another example. One more example that I have, last example that I can give about the nanomaterials and application is neural bioimplants. We are looking to explore this area as well. Neural implants by using these nanomaterials, because these nanomaterials have exceptionally high thermal conductivity, electrical conductivity, and we can use it for neural implants, so we can improve the impurity or those who have low sightedness, these kind of things by using these materials. This is one of the materials research is yet to get start on these areas. So I hope I answered this question about applications where I started from conventional, and the last one is neural implants. I hope I answered this question. So, okay. Artificial intelligence, when I am talking about artificial intelligence, it means we need not to take any decision. They will take decision by itself. Yes, there are composites that are, when it means composite you want, where you want to implement composite. What about structural health monitoring? Have you heard about composite? Yes. Yeah. Hello. Are you getting me? Okay. When we are talking about composites, when we are talking about artificial intelligence, it means we want to introduce some intelligence that it will take decision by itself. So it means, what about structural health monitoring of the structures where the access is not very easy, like in space structures? If we in conjunction having a conjunction between a composite and artificial intelligence, which can be used for structural health monitoring, maintenance and repairing, because still structural health monitoring of composite. I will give you one example. In northern part of Canada, why I'm giving more examples of Canada, because my words were more focused on Canada composites. That's why I'm giving more examples about Canada. We were replacing the metal pipes by using composite pipes, because lifting these pipes to thousands and miles is very difficult. Composite pipes are very good, but how we will maintain it? Who will take care of this? Who will take care that it will not having any defects? I If there is an artificial intelligence that will allow us to take care of these things, I will be more than happy, and more applications will be evolved based on composites. Thank you. You're welcome. Thank you. Okay. Thank you, sir. Thank you. Sure, Professor Verma. Sure, Professor Ravi Verma. Thank you. You are welcome.